Hello, my name is Katsiaryna Mirylenka. Unfortunately, I'm not with you today, but I'm really happy that I'm still able to give my presentation even if it's in a recording. So I'd like to talk today about Siamese graph neural networks for data integration. This is the work done together with Evgeny Krivosheyev and Mattia Atzeni, which are my colleagues or former colleagues also at IBM Research Zurich. So many data can be represented as networks or graphs like social data, economic networks, biomedical data, and so on. And also they are very successfully modeled with GNNs for representation learning or for link prediction tasks and also some other tasks. So for us, there was a question whether we could use graph neural networks for database modeling and database problems. The hypothesis was that we need to put the entities into the context, and then we should be able to use GNNs and build the model representations. I'd like to introduce a little bit the data at our deployment, the data that we were dealing with at the point. So we had families of companies where subsidiaries, headquarters, and so on of the companies were specified. Also, the corresponding locations were there. Also, we had products deployed at each subsidiary of a company. The products were classified in product categories and so on. So this is the data that we had. As you can see, the data is naturally represented via graphs, even though initially it's just the database tuples. So we would like to apply GNNs for record linkage tasks because current data integration record linkage that we use and also that are used in many companies, they are mainly rule-based, they are highly use case dependent, and they lack automation. So we investigate how graph modeling and graph neural networks can be applied to data integration problems. We propose a methodology for leveraging graph structured information for entity matching. First of all, knowledge graph should be created from structured and unstructured sources that we have in our deployment or some other companies have. This knowledge graph is then modeled with graph neural networks to build node representations via information propagation through the links in this graph. The idea is that the nodes that are close in the knowledge graph should be close also in the final embedding space. Also, good news is that the representation of entities that we have in databases, they mostly depend on the natural graph structure of databases, so that we don't need any annotation there. Here, to focus more on the task of business entity record linkage, I should show you the data that we have. This is the reference database. So there are some companies with some structure linking them to the headquarters and so on. Based on this reference database, we can do graph modeling and build a kind of a forest of company family trees where the links come from this subsidiary or headquarter connection. Then we have new entities that come, for example, from use. We extract these entities and we would like to match them against this forest of company trees so that we know from which company family each entity comes. Why have we chosen GNNs? It's because of their very nice properties. First of all, GNN is a deep convolutional architecture with two main components per layer. So there is a bank of graph convolutions and there is a nonlinear activation function. The most desirable properties that GNN have is that the number of parameters doesn't depend on the size of the underlying graph or the number of nodes. And this is very beneficial from complexity point of view, as there is less parameters to learn, and this also makes it scalable to model data using GNNs. Also, because of this independence of the parameters, the parameters are not that tight to the underlying graph, which brings us to the invariance and stability properties of GNNs, and also transferability property, which means that GNN can be transferred from one graph to another if they both correspond to the same graphon properties. So for more details, please advise to this work. This is very interesting work. Also, as shown in Xu et al., GNNs generalize the Westphal-Lemon graph isomorphism test, which leads to the following conclusion. Both the topology of the network and the hidden features of the neighborhood can be learned simultaneously. And this property basically means that GNN can very accurately represent the network data. So the data representation of the learned representation of the nodes are very accurate. This is also the reason why we observe this ample amount of empirical evidence that GNNs are great for different for the networks from different domains. Again, coming back to our problem statement, we have reference DBs, DB with companies. First, we do graph data modeling from this database to build a knowledge graph, and then we match a query company to the corresponding company family. So there are several caveats here. For example, it's a piece of a structure of Cisco systems, and we can see that there are several companies with a completely different name there. So this makes, for example, rule-based system crash because they don't know how to do string matching among these companies, for example. So there is no semantics in rule-based systems, but we are going to bring this semantics through the graph connections. So in the approach that we propose, as input we have reference data, later on there will be a query data that comes through the same data preprocessing pipeline with some data cleaning, maybe use of external knowledge. Then we have graph modeling, and we have these families of companies in our case. And the reference graph goes through the training of graph neural network model. The query graph already goes to the trained model. We get the embeddings, we put them in the space of the companies, and we just find the closest family that we need to match against. Why the conventional GCNs do not fit here? So the conventional graph convolutional network would require label data. Also, this is a classification task. And in record linkage, the number of classes would be huge because each entity would be a separate class, and there are around like 3 million family of companies in the world. And the conventional graph convolutional network would require retraining when the new entities are added, which are not acceptable for the record linkage case. Instead, the methodology that we propose is based on learning distributed representations for every node in the reference graph, this R-star graph, so that nodes representing the same entity are closer in the embedding space and far from irrelevant nodes. So this modeling can be achieved by applying deep metric learning methods such as Siamese networks or triplet networks. So in our case, we are going to use Siamese networks. So again, nodes representing the same entity are closer in the embedding space and far from irrelevant nodes. This is the architecture of a Siamese graph convolutional network that we use. We have this forest of company family trees. Then we have two samples to contrast, let's say. There are two networks that these samples go through simultaneously. And then the signal goes through contrastive loss. Contrastive loss makes sure that nodes of the same entity are close in the space and nodes for the different entities are far from each other. These two GCNs, they share weights. So to train it, we need several positive examples, so several couples of entities that belong to the same entity, and several negative examples or dissimilar nodes. And the question is how to choose the dissimilar pairs in the most efficient way, because potentially you would contrast against all the other entities, but it's not what you do in practice. It's not what you would need to do or would like to do. Otherwise, you need to select the most informative dissimilar pairs to show it to the model. Optimally, you would select dissimilar pairs among close nodes that belong to different entities. So we propose to do clustering of similar entities and then selection of the similar pairs inside the clusters only. So this way we would choose the most representative dissimilar pairs of nodes to show to the model. So here come the datasets that we used in our deployment. These two are connected to Switzerland, and this is the US data. So just to remind that in some company families there might be completely different names of companies. And for example, if you have this one in the training set and these two in the validation test set, then you cannot really, the model cannot really understand that this is the same company. So you need to have some overlap. So we name the first type of this dataset overlap 1. In this variant, we impose the constraint that each name in the validation test set has at least one representative word in common with at least one training example that belong to the same family. So it means that if you have diamas in your validation set, then in the training set somewhere diamas should also be represented. Otherwise, it's impossible to learn. Or some variant of diamas with some other entity descriptor next to it. In the overlap all dataset, this is the easier dataset, and you impose that the most representative subwords are represented in all the training set. So it's like the data set that favors more rule-based methods. So this is how the rule-based methods would work ideally. In US data set, this is similar data as overlap 1, so the most difficult one. Right, this is the evaluation accuracy for Switzerland. The methods that we used as a benchmark for comparison is record linkage system developed at IBM. This is a rule-based system, quite elaborate one. So you can see its performance. Then there is a multi-layer perceptron and graph convolutional network with classification softmax layer on the top. And then a Siamese graph convolutional network come, and a Siamese graph convolutional network with subspace learning come. And you can see that this is the winner in both the data sets. Then also we saw that our query entity that come from the news, for example, it might have only one node, so there is not really a graph to be modeled for GNN. So we decided to do, potentially there are some entity resolution and you could have more mentions of a company in news, but in many cases it's just one mention. So we decided to do some data augmentation, and this data augmentation was made using text summarization, where from a company name we would extract the most representative short name of a company, which is like the most discriminative word in a company name. So this was the text summarization system. It was a sequence-to-sequence system. And we added this data augmentation for all the data sets for training, dataset validation, and also querying. In this way, we can see that all the record linkage systems, they benefited from it. And also like the most performing one, Siamese graph convolutional network with subspace learning is 10% better on the hard data set. Similar results are valid for the US dataset, where the boost from rule-based systems is like more than 18%. Like, yeah, it's like 18% with the short names. Yeah. Okay. I also wanted to show you the 2D representations of 10 important Swiss companies that that GNN can learn, the Siamese GCN. So you can see that these are the families of companies where the dots represent record in the training set and stars represent the records in query set. So you can see that all the queries are correctly specified here. So as a conclusion, I wanted to mention that it's really indeed beneficial to use graph neural networks for record linkage for database systems also. Also, it's great that database systems are naturally organized in graphs, and the information flow can be also organized in a good way without too much supervision. Yeah, this is basically the same. That Siamese GNNs can improve data integration by allowing high automation with close to non-labeling costs. And this work was published at AAI 21 and CML-PKDD 21. Thank you. And if you have any questions, please write to me to this email. I'll be very glad to chat or to discuss this problem. Again, I'm very thankful to be able to do this recording. This is, yeah, great. Thank you. Have a nice afternoon. Bye-bye.